Okay, my friends, I am going to peer review, and I am a peer as just as good as Einstein. I did all of the same nonsense he did. Trust me, I've been through the whole route with this, and I've been doing this for many, many, many years. So I have every right to speak about this, and I'm going to peer review Einstein, and he did not do well. That's just a fact. Physicists use an extremely accurate atomic clock. Well, I'm going to explain the whole thing, I hope, in a pretty good detail. But Einstein took this as, because the atomic clock is not the same in space as it is on Earth, that time slows down in space and it speeds up on Earth. So you age faster on Earth. That's just absolute nonsense. The speed of light is not constant. This is light accelerating. Nobody can deny that. Einstein was wrong about literally just about everything he said, and I am about to explain that. And I would like to have somebody step up and stand up for Einstein and speak to me about what I'm showing. This is light. This is absolutely light. It's from a red laser. This is no protons, no big gigantic particles, no bombs, nothing. This is light, and this is what we did with it. And it shows that Einstein was just simply wrong, that's all. And all the rest of them were wrong too, because they didn't realize light is a dipole. That's right there. Light, and every particle there is made of a black and a white particle. Light is just two of them together. The one black and white particle is an electron. Here we go. All right, this is Fermilab, the one that are looking for the particles that I just showed you. One of the most counterintuitive facts of our universe is you cannot go faster than the speed of light. From this single observation arise all of the mind-bending behaviors of special relativity. Therefore, they're all wrong. I showed you can reaccelerate it, no problem whatsoever. But why is this so? Don Lincoln explains the real reason you can't go faster than light. Well, let's see what you think. All right, here's the key. Remember, these are in a vacuum chamber, and they're oscillating a crystal, and that crystal oscillates exactly the same in space as it does on Earth. Yes, I agree with that 100%. However, on Earth, the closer you get to Earth, the more gravity you have. So therefore, that particle, when it's bouncing back and forth, the gravity of the Earth is not restraining it. When you're near Earth, it can only go up so high and it comes back down. And so it's going to be quicker in the pulsation. So there's more atomic clicks than there is in space, because in space it goes out as, okay, I'm going to come back now, okay, I'm going to come back now. And it just sort of floats around. And you might get 1.5 waves, where here you only get one, because you're closer to Earth and this electron is dropping faster towards the Earth. That's all it is. It has nothing to do with you're getting older or so. It has nothing to do with time whatsoever. It has to do with how fast that freaking clock runs. It's only atomic clock that it affects. It doesn't affect your health or your life or anything else. Although I can't say that doesn't happen. In space, they're finding some really strange stuff happen to people and living things. Now, that's a whole other issue. This is time, and time does not dilate in space. Time is exactly the same. The crystal runs a little slower. That's all. Okay, this just came out. This is 2/16/2022, Sarah Wells, talking about, yeah, well, they finally got proof. The groundbreaking new measurements confirm one of Einstein's most mind-bending theories. All this is that the particles don't go as far up when they're closer to Earth, so they come back quicker, so you get more frequency. When they go up higher, way off from space, nothing's pulling them back, they come slower up and down. Closer to Earth, they come up and down quicker. It's just an extremely tiny difference that would be only a second over hundreds of years, but it's enough to throw off some of the coordinates they have when they're working in space, because that time clock out there is not ticking the same as it is down here. That's all this is the atoms ticking faster down here because it's being pulled back. Out here it's going boo, 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 boo. That's all it is. All right, now I'm going to show you something that's kind of crazy, but it's true. This is red pulsed laser. You have usually red, green, and blue. The blue is extremely fast. The green is very fast compared to the red. And these are the different frequencies that these different crystals push at. And it's very, very specific. That's why they use them for measuring. And they divide the number of pulses by the certain factor, and that gives you so many inches or meters and so forth. However, let's think about it as this is the crystal pulsing. This is nothing more than a frequency that Einstein's talking about. Boop, 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 boop. And this frequency gets faster and faster as you get closer to Earth, because it pulls the particle down. Now, we can accelerate the light, so obviously he's wrong about that. And what are we accelerating? We're accelerating a particle, and almost nobody knows it's a particle. I mean, they know there's particles within protons and in these gigantic pieces of matter, but they've seen them, but they don't realize that they are literally these light pulses. And the particle is back here. The field that it creates is in front. That's the field. Now, we put it through a venturi, so we accelerated. We pulled that particle right out of its own magnetic field. This is just phenomenally unbelievable, but it was just an accident, to be perfectly honest with you. The venturi, which is a single slit, is so tiny that it will only let the white come through. There's black and there's white. All right, and you get down to a spot that big, the black ones can't crush. I've shown this a zillion times. They come around and go here. But in the meantime, as they're all coming just like this. They can't get through. So they come around the outside, and they come back in back here. Now, I think they're all bazillions of them waiting here to get back in. But in this meantime here, we have raw energy. This is what bothers me, that nobody will pay any attention to this. And this right here is free energy. We did nothing whatsoever. We added no energy whatsoever to get that effect, which is to create the muon and the electron neutrino. And then electron showers. Whoops. Let me take that off of there, and then we will see what happens in the other types of light. All right, because, by the way, this is a gouge on my screen. I'm going to get a new screen. Somebody offered to get me one. Believe me, I can get one, and I appreciate that offer, though. Now, this is where they bang together, and this is where they divide, and this is where they come back. Between here and here is the division. These are the Higgs fields they've been looking for a bazillion years. They call it the God particle. Those are Higgs fields. We can create them coming out of our ears. That's the particle. Cornell reported on this long ago. They saw them, but they had no idea how to do it again. These are 2p, which is the white ones, 2p's, and 2h's, which are the holes. And these are what we would call electron neutrinos and muon neutrinos. And then when they hit the venturi up here, they divide it, shown it a bazillion times. Here it comes again. Now, here we are with that light. It would have never gone any faster than about like this. And it would have just kept going like this forever. And very little interference in front of it until we created that venturi I showed you before, and that forced that light to squirt through here. And it's because the big black balls are almost like slamming the white through there, and the white can crush and come right through there, and it does. And the blacks go all the way around and come back here. Right there, that's raw energy. It's supposed to be 200 times the input value here. 200 times, that's just enormous. And I can't dispute that. We hardly have any impact here. These waves here are coming back from here. These are reverse EMF, reverse electromagnetic flux lines, fields. And going this way, we really didn't have a whole lot going on until it hit here. And then just look at the power. Just look at it. Just think, just let your mind understand what you're looking at. We're shooting back energy, hitting more of these. These are all over the place. You just can't see them because they really don't impact anything. Now they're impacting because this is pushing back at it. Everything is push to shove, push to shove, push to shove. If you're not pushing against anything that's shoving back, you just keep on going. This is a whole different issue. And they know that. I'm not making this up. This is not me that's talking. This is CERN and Fermilab, and I think they're kind of embarrassed that they could never do this, and we can. There's the black ball. There's the white ball. There's the black ball continues. There's the white shower that comes from right here. It is. I showed it. There's no question is happening. This is zero question. That is fission. They divided. Zero question. That is fusion. They came back together. Zero question. These balls literally never change size. You see the size of them? They're all basically exactly the same size. They can't get through that slit. It's so tiny. It's as simple as that. Cold fusion on a desktop. And I can show you why those particles can squirt through, and here's why. The white ones can crush. The black ones, they're just this the size of them. That's it. Case is closed for them. And they are heavy, and I can show that in a nuclear bomb. When you see it go off, the first thing that happens is everything in front just burns. That's because these are the ones that are hitting first. And they have no weight to them, basically. They have a burn to them. They just burn like crazy. And then all of a sudden, these come behind them, and the house goes flying, but it doesn't burn anymore. And then the nuclear core is now almost solid dark matter, and it wants all these white ones back. And everything turns around and comes back. Shown that a bazillion times too. This is what's going on with light. Let me show you how this particle manifests itself, and then how it divides itself. And I've shown you how it divides and comes back, but let me show you the process of it be actually manifesting itself. And then I'm going to show you the red versus the green. Alright, this is the whole shooting match where the light is coming in from the left here. And that's the Venturi. Whatever is in line with the Venturi glows. The other ones don't. You know, there's a lot of light coming through here and down here, but not in line with the Venturi, so it doesn't glow the same way. Now, don't forget, that's just nothing. Scratches. Now, let's see from the left where it comes in. Why are these flat like little Oreo cookies? They're a little flat on black on the top, black on the bottom, white in the middle. I really can't tell you why. But I can tell you that as they start to stack up, they get brighter and brighter. And then the whites separate away from each other. It's almost, I'm sort of trying to understand it. Because they're obviously becoming energetic. Up here, there's nothing. There's no push to shove up here. There's a push to shove down here, and then they start to they twist up and they go this way. And I'm seeing this happen, and then this happen. You can see the same thing, and you can see that this is not as bright as this is, and you can see it doesn't have the little spiky thing sticking up as this does. So this is really starting to glow. Now the next wave is the impact right here. And that is where the particles divide. As I showed you, the blacks and the whites, that's fission. And when they come back together, it's fusion. Because when they divide, it's fission. Anything that comes together is fusing, it's fusion. And that is what they're looking for free energy. And I think we can do it. All right, now here's where we got the green, which is much more powerful than the red. However, it is the identical same particle. There's no difference between the particle. And you can see the spikes coming up. This is where it's beginning to flip. This is caught midstream in the flip. And that means this white will go to the back, and it's coming to the back now, and that white will go to the front. This one's overcharged, and it has to flip. And the red ones, I've never seen the flip, but let me show you a couple other shots. But anyway, you can see this is the same, a trail and a poof, she slams. Now the other thing I want you to take away from this is you see how they're swirling away from each other and setting up these stripes? That is what they call the interference patterns. They're not interference patterns, those are repulsion patterns. These whites don't want any other white guys coming this way. So they set up a border zone, a buffer zone between them. So they push to shove, push to shove, push to shove, and that's what they do. And also light spins. So that's another factor that leads to that type of an effect. See the red one, I don't see any transition like a flip, but I can see the white is behind in this one, and it's in front here. Now, I believe this is the same particle, because you see more than one particle, well, you see the same particle several times in this one flick. And I'll show you the blue. Well, hold on. All right, this is a different color, which is fast. This blue is faster than the red or the green. That's why we really can't see the particles as well, but you can see they're very fast and they're spinning. They're drifting to the left. That means it's a right-hand spin. And you see that at the bottom, they're really balled up, real tight, and they just slam and slam, 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 and then they're starting to spread out a little bit, and they're opening up a little bit, and you can see, you're actually beginning to see the separation of the particle nature of it, the two whites. Blue is extremely, I didn't get much blue interactions, to be perfectly honest. This is the best I've got for blue. Well, let me show you one other blue one. All right, this is through glass. You see the rise of this little, that's the laser in the blue. And all of these little dusty looking things in here, they're particle reactions of some sort. I mean, they obviously. And you can see they're brighter as they're closer to the source, and they tail off as they come further off. But you can see how extremely quick that impact is in the beginning, just as I showed you before with the spreading out, and then we could finally see the actual break in the particles. Well, you're not going to see that here, I don't think. I don't know. But this is the tip of the wave of this particular one. You can see that it's just starting to spread out. Eventually, it'll get absorbed into the particles that were in this case, glass. Now, that's why light goes through glass. It slows down when it goes through glass. There's no question whatsoever. It's being absorbed. Anytime you see something glow, it means that whatever it's hitting is absorbing some of its energy. That's as simple as that. Only this is extremely powerful. Now, let me show you the green and the white. All right, this is the green. This sucker really whacks. Now, that's going through the venturi. And it just comes way out here before it really even hardly impacts. And out there is where we're seeing the particles show up again. All right, the black is reattaching to the white. That's this interaction here. In between here, there's nothing but white. You can't really see it all that well, but believe me, it's almost no interactions happen until out here. So this is raw. This is literally raw energy, absolutely raw energy. Now, let's look at that between that and the red. All right, this is, you see how far out the green goes before it impacts? The red impacts pretty quick. Now, this was the red laser. You see it's dull looking. Look at that baby. Now, why is the red coming down this way if this is a laser? Well, why doesn't it just go swoosh this way? Well, this one is coming through on here, right at the same time, through the same slit. That means who can push the other guy out of the way? Well, this guy can. Get out of my way. And it goes this way. And not only that, it makes the light particles literally spin in circles. You see them? As it goes by them, it twists them and spins them. It turns them into little vortexes of particles. I'm not kidding you. I think I have a better shot of that. Hold on a second. Okay, yeah, this is a little better. Now, again, there's the red, there's the green. Now, a little bit of red snaked up in here by accident. Somehow got twisted and thrown up in here, but that's the tiniest little bit of red. Other than that, all the other red goes down. There's an impact zone here where they both interact together. And then the green makes its collision way out there where it normally would, except this was excited in front of it, so it had to get that stuff out of the way. Now, when it pushed it out of the way, look at what it did. It turned them into little vortexes of spinning particles. You see them? They're spinning here. That's that particle spinning in a circle. This is just crazy stuff. These are light. This is light. That's what Einstein said. Light is light. Everybody says light is light, and it is. I can tell you that particle is identical to that particle. Only this baby here is on steroids compared to that one. See, I told you, light spins. This is the laser coming through here, and it's starting to dissipate out and wash back into normality. Here it's highly excited. You can see them all. They're all spinning basically at the same spin, and by the time it gets down here, they're basically absorbed. All right, but you see back here, this is just after it came through the venturi, a little past as it starts to really concuss. Anytime you have something brighter than something else, it means it's glowing more. It means it's more energy. Simple as that. And that's why on the edges, you don't see that kind of energy. The energy is in the center. All right, they always talk about light being a particle and a wave, and that is true, it is. The particle creates the wave. So what do we have here? This is light. It spins. It spins. You can see it spinning. If you were ever you ever see a drill bit, that's a spinning drill bit. It's drilling its way through the venturi. Here's where you have most of your concussion. Here's where you get these separation patterns, push to shove, push to shove, push to shove. That creates these strike patterns. It's not so, this is a single slit, so don't worry about what they talk about interference patterns. It has nothing to do with flopping waves. It is pushing and shoving, pushing and shoving. Now, what do we see here? That is what they call frequency. And they say, well, light is a wave. Well, yes, it is. But it's a spinning particle that creates that wave. Spins up, it spins down, it spins up, it spins down, it spins up, it spins down. But that is the wave. All right, so all it is a field in front of it. As it goes forward, that field spins around a circle. That's what those Higgs fields are. All right, these are the Higgs fields. These little circular disks and all these little pulsations. That's that particle flipping as it's going spinning forward, concussing back with reality. From here, this is coming right at us from the venturi. Remember, on the other side, we had all that white and the black went around. Well, this is the black coming back, only it's now turned into a polar particle. That gives us this field effect. Now, between here and here, though, is like just raw energy. And then we have the Higgs fields. Now look at this puppy here. That is the only time I've ever seen this. And I believe what happened here is it concussed with one of these and created, it looks to me like an antiparticle. Now, there's another thing to see here, is this started red. They're all red. Red is the frequency that they're supposed to be. Why is that one turned purple? Why is this one orange? Well, what happened was this one here is being crushed on both sides. I have a better shot of it, and it's squirting it out like you squirt out a piece of toothpaste, and it's accelerating it, which makes it increase its color value into purple. All right, they started all out red. Red is a frequency, so all of a sudden now we have purple, which is a squirted out frequency. So we started with like this, and we pinched it, and it went out like that. That's what this is. Okay, now I can't be 100% positive of this, but I'm pretty sure this is the same white particle, because all of the rest of them came through in a disc shape like this. This has some structure to it. What that is, I don't know. I think it's spinning backwards, because there's a right-hand rule supposed to spin this way and throw its energy out. Well, if it spins the other way, it drags its energy in, it turns bright, but then it hit here, and what's it doing here? I have no idea. But I can see it's restructuring itself, and it's tipped off something. And the more it glows, the more energy it has. So this is a pretty energetic little particle. But it's coming forward. This is very energetic too. So anything that's coming forward is energetic, but this is also energetic. Now, in what manner? Why? So this brings a whole new realm to everything. It just gets deeper and deeper, but they always talk about antiparticles, antimatter. Well, who knows? Now, check this out. You know about the black and the white particles, black and the white four-bangers. This is a slit here. Now, you see how it's a little tight here and it's a little wider open up here? The slit is just a venturi. It's just a slit, but it has a shape to it so that it crushes the particles. Coming out of here, you can see all the black ones. Black is everywhere over here. Black, 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 black. And the white, obviously, is with it, and they are combining back together here, glowing like crazy. Well, what's going on over here? Totally different, 100% different. Take a second and look at it, because it's so much different, it's hard to understand at first. And a second, probably a third too. What are all these little lines? The hell is all that about? You don't see them over here. Why? How come there's no black spots over here? I mean, literally there's none. They're all over this side. We know that all these particles have a black and a white. This is only white. Pretty interesting to me. Can we duplicate that? Or is there any value to that? Well, I can tell you what, there's a value here from what we started with, from the green laser coming through that. It's just this enormous amount of energy, and then it comes back together. But this is just very, very, very interesting. This is almost like separating out the values, almost saying bring all the black stuff over this side and all the white stuff over this side, because the white again does not have a big banger impact. It's just, you could see them just floating through there. They're just floating through there. But anything in front of it is going to burn. That's all literally burning in my mind. That is just burn. This is slam, bam, 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 and make it just glowing like crazy. This is burn, 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 burn. And when I say burn, 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 nice and simple, it's exactly what you see in the atomic bomb, as I will show you right now. All right, you know, in my model, you have a dark particle, and this never changes. This is never going to change. Then you have the fluffer, which is the electron. It can get big, it can get small. And it's approximately 1,837 electrons make a proton, these particles, somewhere around there. I think I figured it out at 1839, but the protons are an odd number, 1837 or 1839. Neutrons are either 1838 or 1840, but they're neutral, so they don't want to attract or give up. The protons want another one, so that's why they're attractive. They're an ionized nucleus, basically. Now, we have this, and then we have that. That's what a photon is. When that bangs into something, if it doesn't hit it as hard as we put it through the Venturi, it just bounces back, and it comes back a little bit different color, would depend on what it hits. Through our Venturi, we actually made them separate and caused the electron flood. So, what does it look like in a nuclear blast? Let's see. Because the first thing that's going to come out is the white. And then after that, just shortly after that, the black comes and impacts. This causes the house to explode. This just causes it to burn. And I can't really account for that. But all I can tell you is this does not seem to have any push. Let's go with push. It's got to have some kind of a mass. It's burning the damn thing like crazy. This one here, though, has no burn, and it has a lot of push. So this one here is the heavy bowling ball particle. This is like a flamethrower particle. Watch what happens here at the house. Now I have this running a little slow on the playback so we can watch it. Here goes. I got the sound off. Now it's going to be the blast goes off. Okay, so here we are. Boom. Now what? I'm going to stop it just so you can see. It's just combusting. Not a single thing has blown back yet. Watch. It's just burning, 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 and all of a sudden the black ones will hit. See, it's just burning. And it's literally burnt almost everything that's burnable. And all of a sudden, pow, comes the black ones. Boom, there's the black ones. Now watch what happens. It'll start to come back. See it all turn around and come back this way. See the dust and everything's coming back? Why did that happen? That happened because back where the explosion took place is almost completely black particles now. And they want the white ones back. And they're going to go back.